All right, we're going to look at section 6.7 now. This will be the last section in chapter 6. It's titled Assessing Normality. And what we're going to do in this lesson is to evaluate a set of data to determine if that set is normally distributed. Oftentimes in our problems, we've had a requirement that the data has to come from a normally distributed set, but yet we just say assume that it is, or the author tells you that you're given that it is. Now we're actually going to be able to come up with ways to look at a set of data and decide, is it normal or not? There are three things that we're going to kind of look at to help us with that. The first is to construct a histogram. And we're going to look at that histogram to see if it appears to be bell-shaped. We will reject normality if the histogram departs dramatically from a bell shape. It doesn't have to be perfect. We're looking for the general shape of a bell curve. But if it's obvious from the look of the histogram that it's not, the data does not come from a set that has a normal distribution. 2, we want to look for outliers. It says to reject normality if there is more than one outlier present. Remember, if it's a normal curve, we have these tails in which there's virtually no data in the tails. It says just one outlier could be an error or the result of chance variation, but be careful because even a single outlier can have a dramatic effect on the results. So we want to try and identify outliers. If there's more than one, we will reject normality. Sometimes even if there's one, depending on where it is, it's kind of subjective, you may reject normality there too. The third thing we're going to look at, and this is the one that's going to take a little bit of technology, is a normal quartile plot. So if you construct your histogram and it looks basically symmetrical and looks kind of like a bell curve, and there's at most one outlier, we're going to use technology to generate a normal quartile plot. We're going to use the following criteria to determine whether or not the distribution is normal. Now it makes a note to say this criteria can be used loosely for small samples. So we don't have many pieces of data. We can kind of use the histogram, the normal quartile plot. But if we have large samples, these are pretty good ways to check normality. So the first criteria we're looking for when we do a normal quartile plot is the population is distributed normally if the pattern of the points is reasonably close to a straight line and the points do not show some systematic pattern that is not a straight line pattern. The second criteria we're after is if it's not a normal distribution, then that normal quartile plot the points on the normal quartile plot will not reasonably lie on a straight line, and that the points show some systematic pattern that is not some straight line pattern. So let's spend a little time exploring normal quartile plots and some of the things that we might see. So let's take just a second to talk about what a normal quartile plot is, sometimes called a normal probability plot. It's a graph of points, so we have an x-coordinate and a y-coordinate, where each x value is from the original set of sample data, and the y value that goes with it is the corresponding z-score that is expected from a standard normal distribution. So we end up with an xy coordinate where the x is from the set of data and the y would be the corresponding z-score from a standard normal. Now we're not going to calculate all of these. We're going to let technology help us with these normal quartile plots. But what we want to do is be able to look at the corresponding plot and decide, is it normal or not? Remember, what we're looking for is a straight line. So let's just imagine that we do a normal quartile plot. We go to our technology, and the resulting graph gives us something like this when we plot the points. We would have to decide, does that look reasonably close to a straight line? That is, could I take and draw a line that reasonably fits the data? In this case, the answer would be yes. If our normal quartile plot looked like this, we would say that the set of data is probably or the population is probably normally distributed, because the points that come from your normal quartile plot end up kind of lying on a straight line. Let's take another example here, and I'm going to draw a histogram first. Let's say that it's a uniform distribution. Remember, in a uniform distribution, we ended up with something kind of like this, where our histogram, let's say this is one bar and a second bar and a third bar, and instead of having a bell curve, we have a uniform distribution. This is tricky because the normal quartile plot that comes from a uniform distribution may end up looking like this. I'll do my best here. It may look like that. Now, we could look at that and say, well, it looks like it kind of fits a line, so it's probably going to be normal. But that goes back to the second criteria. It's not a normal distribution if the point shows some systematic pattern that is not a straight line pattern. In this case, this kind of looks like it fits a curve. And if we were to plot the points, it kind of fits this kind of a curve. So in this case, just looking at the normal quartile plot, we might assume that it looks pretty linear, but if we looked at the histogram, we would see that it comes from a uniformly distributed set of data, not normally distributed. So it behooves you to look at both the histogram and the normal quartile plot. So this one can be a tricky one at times. This will catch you once in a while. The third example would probably be a little more obvious. Oops. And let's say we have a histogram and it looks something like this, where we have a whole bunch of stuff here and then not much out here. The normal quartile plot of this would look, actually, it would look something like we've got a whole bunch of things right here. Got a lot of points there, and then not very many as we move on. And we could see that this would not fit a line. I don't think we could get a line. Or maybe there'd be a line, maybe something like that, but it doesn't really fit these pieces of data. So maybe the line would be something like this. Well, that really doesn't fit. And again, we can look at the histogram and see that's not bell-shaped whatsoever. It's not symmetric at all. So putting the histogram together with a normal quartile plot, we can decide and make kind of a subjective but yet educated guess that the population must be normally distributed. All right, let's take a look at this set of data, the actual high temperatures for September. And we want to evaluate whether this population, these temperatures, are normally distributed. So in order to assess normality, first of all, we want to examine a histogram. We want to look at a visual of it. We're looking to see if there's some symmetry here, if it's kind of a bell-shaped curve. So in order to do a histogram, I would need to look at all the values in here, and I see a minimum value on the last day of September of 62 degrees and a maximum value of 85. So what I'm thinking to build this histogram is that we have a range from 62 to 85, and including those, that's actually 24, a range of 24. It looks like 23. The range would be 23, but actually it would be 24 data points we'd be looking at. And if I want to put them into 6 bins, then each bin would have to be 4. So my bins are going to be 62 to 65, 66 to 69, 70 to 73, 74 to 77, 75 to 81, and then actually I take it back. That's 78 to 81, and then 82 to 85. So I'd want to start to build some tally marks here as to how many temperatures fall into these bins. And I'm going to take a second to pause the video while I do the tallies so that we don't have to waste time with that. Okay, so I've done my tallies, and it looks like there were 3 numbers that fell between 62 and 65, 2 numbers, 6 numbers, 8 numbers, 9 numbers, ran out of room, and then back to 3. So if we looked at our histogram, and if we imagine looking at it on edge, so if we turned our head and looked at it, does it look like it is symmetric or bell-shaped? And I think the answer is going to be no here. It's not got great symmetry. Obviously, there's fewer days of the lower temperatures, and the higher temperatures are kind of grouped in the middle. Doesn't have great symmetry. It isn't necessarily bell-shaped. So I'd kind of tend to lean towards a no here. Are there any outliers in this case? Not really. There's no temperatures like we didn't have a day that was 106 or 31 degrees in September that would mess up these readings. So the last thing we need to do is look at the normal quartile plot. And let me show you how we want to do that. First of all, we want to get our graphing calculator, and we're going to use our TI-84 Plus. You can either use it on your tablet or use your actual calculator to do this. So what we need to do is we need to get these temperatures in for the month of September. So I'll come over here where I can see my temperatures. In order to do that, we're going to hit our stat key. Okay, that's the key right here. I'm trying to wave my cursor over it. We hit stat and edit. So let's just hit enter. And it's going to bring up a list. And we're going to put these numbers into that list. And if we wanted to, we can actually name our list using the alpha key. That's the green key. So if I wanted to, I could call this temperature. So I could hit alpha T and then alpha E, alpha M, gotta find it, and alpha P. So I actually named my list. Oh, let's back out of that. I think what I was trying to do was put that into the actual list value. Let's just keep it list 1. There is a way to rename it. I'm not going to mess with it right now. But let's put our temperatures in. So I'm going to start by putting in the first data point is going to be 80 and hit enter. Now it's asking me for the second one. We're going to do 77 and so on. So I'm going to enter all these in here. I'm going to pause the video and get them all entered, and we'll go to the next step. Okay, and as you can see, we got them all entered. Looks like I made a mistake on the 29th. That should have been 66, not 6. So I can correct it. If you need to correct anything, you can just go up and down through the list, check all your points, and correct anything that needs corrected. But I got all 30 of those data points in there, and now we're going to let the calculator do our work for us. Okay, so here's how we're going to let the calculator do this for us. We have our list of data values, so we're going to go second and then y equals, which is stat plot, that's in blue, so we're going to go second and stat plot. We want to make sure that only plot 1 is on, and in this case plot 2, 3, 4, don't worry about number 5, but 2, 3, and 4 are all off. So plot 1 is on, and we're going to go enter. And we want to make sure that the type of graph that we're doing is clear over here on the right, looks like a line. What that's going to do is that's going to give us a normal quartile plot. So once I have it plot 1 on and have selected the right type, and the data list is L1, that went in there by default, it's the only list we have in there, we're going to quickly look at it by going zoom and 9, zoom stat, and there is the normal quartile plot. Remember, in a normal quartile plot, the x values were your data points, the y coordinates were the z-scores that went with that, assuming it was a standard normal distribution. And we can look at each of those points by using the trace key. And the first data point, 62 degrees, that was the one that was on September 30th. It had a z-score of negative 2.12. And if we use our arrows, we can go between the points. We can see that a 70-degree temperature had a z-score of negative 0.902, and so on. We kind of move through here and see where we switch from positive to negative. So right here, it looks like we went from a negative 0.04 z-score at 76 degrees, a positive 0.04 z-score at 76 degrees. It's kind of interesting how that happened, but it has to do with how those are calculated. And by looking at that, since 76 was 0.04 and 76 was also negative 0.04, that probably tells us that the mean value is 76 degrees in our normal distribution. So what we're really looking for is, does this look like it's linear? Does it look like it would fit a line? And again, we have to use some subjectivity, although the histogram, remember when we looked at that, we thought not necessarily bell-shaped and sort of symmetric. It might fit a little bit of a bell curve. We weren't really sure. When we look at the normal quartile plot, it sure looks like it's a lot more linear than I would have expected from the histogram. So I would say in this one, if we're deciding whether the data comes from a normally distributed population, I would probably tend to lean towards yes, based upon our normal quartile plot. It looks fairly linear. Okay, in summation, this lesson was on assessing normality, trying to look at a set of data to determine if the set of data or the population is normally distributed. Remember, we wanted to look at a histogram. Can we tell by a histogram what the shape of the curve might be? 2, we had to identify were there any outliers. If there was more than one outlier, we were going to say it was not normal. And then finally, looking at a normal quartile plot and determining if it looks like it has a linear relationship, then yes, we would say it comes from a population that is normally distributed. If it wasn't linear or had some systematic pattern to it, we decided it would not come from a population that is normally distributed.